So we're about to embark on a series of videos that go into the origin of the elements, the origin of planet Earth, and the origin of the oceans. In order to do this, we need a bit more background here about the nature of isotopes. So in this video, we'll talk about the definition of an isotope and how that's distinct from an element. There are stable isotopes and there are radioactive isotopes in the world, and we'll talk for the radioactive ones about how to estimate how long-lived they are based on their half-life. For the stable isotopes, they tend to have more neutrons and protons, and we'll look into the forces that are behind this. So in the last video, we talked about how the different elements are organized on the periodic table here, but there's actually a whole other dimension that basically describes the matter in the universe that we can't really encapsulate in this table of the elements. This extra dimension represents the fact that individual elements can come in multiple flavors, or isotopes. So in the last video, we talked about how this atomic number here, 1 for hydrogen, is unique to every element. If an element has 1 proton, it's hydrogen. If it has 2 protons, it's helium. That said, there are different versions of hydrogen out there that have the same number of protons but a different mass in the nucleus. And the way that this works is the number of neutrons can change, and it doesn't affect the fundamental properties of that element. So the most common form of hydrogen in the universe is H1, like the highway. And it's got 1 proton and 0 neutrons, and it represents 99.98% of hydrogen out there in the world. That said, there's a rare form of hydrogen called deuterium, or H2. It's got 1 proton, 1 neutron, and it basically forms 0.02% of all hydrogen out there. So it's very rare, but it's twice as heavy as normal hydrogen. And then lastly, there's one extra version that's even more rare. It's tritium, or hydrogen-3. It's got 1 proton and 2 neutrons. So when you're looking at the periodic table and you see the decimal places here, this is often a representation of the relative abundance of different isotopes and their relative masses. So the fact that this is a bit heavier than the mass of just H1 reflects the fact that there's a small contribution of deuterium here. So this tritium here in particular is what's called a radioactive isotope. So unlike H1 or H2, which stick around since the beginning of the universe, tritium here will decay pretty quickly, in the grand scheme of things. It has a half-life of around 12 years. And so when tritium decays, it decays into this product, helium-3. Helium-3 has 2 protons, but 1 neutron here. So you can see there's a switch between the 2 neutrons in tritium and the 2 protons here. So this is one example of the 2 main types of radioactive decay. These are called alpha decay and beta decay. The disintegration of tritium is an example of beta decay. So in beta decay, you have a neutron being converted into a proton and an electron. There's this less common form called beta positive decay, which is basically the reverse reaction when you have a proton and an electron coming together into a neutron. We'll talk about cases when that can happen, but it tends to be less common. But anyway, tritium going to helium-3 is an example of beta minus decay. And you can see here how this kind of checks out here. So a neutron basically has the same mass as a proton and an electron combined. And obviously when you combine an electron and a proton here, the charges balance out. And so this beta minus decay sort of balances mass and it balances charge. I'll also mention that free neutrons out in space outside of the nucleus don't last very long. They are also radioactive, and they also undergo this beta minus decay. So if you have a free neutron floating around in space, it will decay spontaneously into a proton and an electron, and it'll form hydrogen. So one of the remarkable things about radioactive isotopes is that they decay very regularly. So if you have tritium, it will disintegrate on a very dependable time scale, and we can sort of talk about this time scale in terms of a half-life. So a half-life is kind of what it sounds like. It's basically the amount of time that needs to pass in order for you to lose half of the tritium you started with. So if we start off here at 1, then we can figure out what the half-life of tritium is by finding out at what time we go to basically 50% abundance of our original tritium. So if we start off with 1 pound of tritium, we wait until we have half a pound left, figure out how much time has passed. We look and it's around 12 years. That's the half-life of tritium. If we were to wait another 12 years, half of the remaining tritium would disappear again, and so we would have 25%. Another 12 years, we'd be at 1/8 of the original amount, or 12.5%. So this is never going to really hit zero. It's just going to cut in half and cut in half and cut in half every 12.5 years. That's sort of what defines a half-life. And then you can see sort of, just as we're losing tritium here, we're gaining helium-3. So after 12 years, half of the tritium has converted into helium-3, and this is going to, approach the total amount of tritium that we had, but it's never going to hit exactly there because we're always going to have a tiny amount of tritium left. So this is an easy example because it's hydrogen. It's the first element on the periodic table, but there's actually a really weird history of using tritium to understand the oceans. And this comes from the kind of sad history of nuclear weapons testing throughout the Pacific. When nuclear bombs are detonated, a whole lot of tritium is released into the atmosphere, and that hydrogen basically reacts with oxygen to form water, but it's tritium water. And that rains out on the oceans and kind of labels the surface of the ocean with this tiny amount of radioactivity. This isn't, in terms of the consequences of nuclear, explosions here, the amount of tritium in the oceans is pretty tiny and insignificant from any kind of ecosystem health. But it has been used to understand how fast the ocean mixes. And that's because it's decaying on this predictable time scale. So for instance, this is an ocean section across the North Atlantic Ocean. Here's the east coast of the US here. Here's the west coast of Africa, and up here, this is sort of Portugal area here. You can see here there's sort of a lot of tritium in this water here, and then less in the deeper ocean. But if you look at this bottom panel, this is helium-3. And so you can see there's this high amount of helium-3 in the midwaters where there's actually not a lot of tritium. And what that means is that these waters here at around 1,000 to 2,000 meters, were at the surface of the ocean in the 1950s. They received tritium, but then, in the time that's passed, that tritium is decayed into helium-3, and so we can understand a little bit about how the ocean mixes based on this history of input of this radioactive element or radioactive isotope. So how do we think about other isotopes? The most common way to sort of view all isotopes together, kind of like the periodic table, is the table of the isotopes. So here one axis is the number of neutrons in a nucleus, and one axis is the number of protons in a nucleus. So for instance here you can see all the hydrogens lined up in a row here, H1, H2, H3. The two stable isotopes of helium are here in blue, helium-3 and helium-4. There's a couple really, really rare, really short-lived isotopes of helium. These are around for nanoseconds, if that, probably a lot less. So yeah, in this in the next slide, you'll see that they're really short-lived isotopes that have been measured but aren't really relevant to the world at large in either green or white here. So let's zoom out a little bit. Essentially, you can see this sort of valley of stability emerge. This is the path of stable isotopes, where you are increasing the number of neutrons and the number of protons. If you have way too many protons, you have an unstable isotope. If you have way too many neutrons, you have an unstable isotope. So it's really only these isotopes that are being stable here. I should mention here that this this yellow thing here, this is a free neutron space. So this has a half-life of around 10 minutes. So zooming out, once again, this is the entire table of the isotopes. The color is a bit different on this slide. So the valley of stability here is marked in black. And one thing you can see is the fact that this valley kind of turns. It's a steeper slope here at the start, and then it kind of flattens out a little bit. This is reflecting the fact that the stable isotopes are requiring more neutrons in order to be stable. So for instance, you can see here when the number of protons, or Z, is 20, you have a stable isotope when the number of neutrons is 20. So then when you keep moving up here, you only find stable isotopes here in this black when you have 82 protons and a much greater number of neutrons, so 126 here. So this is just describing this trend in stability of matter. What's going on here? Well, we can think about the two forces that are basically fighting against each other in terms of what makes a nucleus stable versus unstable. So obviously, when inside a nucleus, right, you have all these protons jammed together in a pretty small space, and if all these positive charges, they're going to repel each other, right? So one of the main forces that contributes to nuclear instability are the repulsions of these protons here. So the protons sort of want to be far away from the other positive charges here. The sort of counteracting force that holds some nuclei together are this what's called a strong nuclear force. This is this association where at a very small distance there's this beneficial interaction between protons, neutrons, even between protons and protons, and this can overcome the repulsion of protons in a nucleus. But the reason that for a really heavy nucleus that has lots of protons in it, you need even more neutrons to kind of pad out, to sort of increase the space between protons, so there's a bit less repulsion and a bit more strong nuclear force here. Okay, so before we close up, I just want to mention the last sort of type of radioactive decay. This is alpha decay. So alpha decay was discovered first, that's why it's called alpha. And essentially this is really found in these large unstable nuclei, and they decay to a smaller, more stable nuclei by ejecting what's called an alpha particle. An alpha particle is essentially the same thing as a helium-4 nucleus. It's got 2 protons, 2 neutrons. So here you can see there's a 1-to-1 ratio of neutrons and protons here. So if you have a bit too many protons, you can become more neutron-rich by ejecting an alpha particle. So that's sort of what emerges in these really high mass nucleus. They become more stable through this process of alpha decay. Okay, so just to wrap up the important points of this video, we talked about the difference between an element and an isotope, and we talked about how to measure the half-life of radioactive isotopes if we have a bit of data. We also sort of looked into the fact that heavy elements tend to have more neutrons than protons, and that's sort of a common feature of all matter in the universe, as seen through the table of the isotopes. So next, we're going to look at the formation of the elements and how this sort of sets up the initial conditions for our planet and our oceans and life on Earth.